Hello, my name is David Smith, and today I'll be presenting work on behalf of the vSense research group in Trinity College Dublin, and the paper is entitled Semantic Crowd Retargeting, Implementation for Real-Time Applications and User Evaluations. This work investigates how environment semantics can be used for retargeting crowds between scenes. The idea is to be able to take crowds from one scene and reuse them in another, and semantic information is used to define crowd behavior. And the diagram on the left illustrates this. The idea is that if we swap the semantic environment for a new one, that the crowd behavior should respond to this and should be defined by the semantics. Similarly, if we use a different crowd with different people, their behavior should still reflect the environment semantics. The first question that we had to answer was how to process existing semantic data for use with our framework. There's some difficulties. Semantic data comes in forms which vary in structure. Therefore, we need a uniform way to store and process this data. AI modules need to know what fields are expected and how they are represented. And new sources of semantic data may become available, and these need to be integrated with existing data. And an example that illustrates this is shown here. So we have a virtual asset shown on the left, which is the campanile in Trinity College Dublin. Also shown are two different ontologies which can describe this asset. So you can see on top we have Dublin City and annotated LiDAR point cloud. And in this ontology we have building, facade and roof. And then on the bottom we have a classifier trained on the cityscapes dataset. And you can see that under construction we have building. So the question is, given that we have multiple sources of data that could potentially be used, how can we kind of resolve them and pass them into the AI decision-making modules which need a fixed representation? So the solution we came up with is to use JSON schemas. These offer a consistent way to structure semantic data. They're human readable and machine parsable. They provide structural validation of the data to ensure consistency, and robust and efficient libraries do the heavy lifting. So you can see here an example of a schema and a corresponding instance. We use this to read in door positions, and this was passed into a spawner script for our agents. And this ensures a consistent format which is agnostic of the actual source of the data. So any existing data needs to be transformed into this format, and then it will integrate seamlessly with the existing simulation. And we were able to process about 700 door locations automatically for this, which greatly sped up the process. So the process is visualized here. We have door locations which are semantically labeled in our LiDAR dataset, models registered, and JSON locations, door locations are written in JSON format. Then this data can be imported to Unity, validated against the schema, and then used as part of the simulation. Given that we have this semantic data structured in this JSON format, the question is then how can we use this to drive crowd behavior? So we created a potential field module which is specifically integrated with this approach. The implementation specifies a piecewise quadratic conic function which tilts the surface towards the goal. We have Gaussian distributions providing bumps, and gradient descent is applied to define trajectory. We take a linear combination of the vector from the agent to the goal, the gradient and momentum term, in order to update the agent's position. And finally, we also add a piecewise linear regression to reduce the number of points while maintaining trajectory. So you can see here that we have many redundant points, and we've been able to compress them by a factor of about 20 using this approach. We then integrated this with the JSON schema so that the potential field can read in obstacle locations directly from the schema. So once the scene is annotated with obstacles, one potential field can be created for all agents, and they will know to avoid obstacles. So then retargeting is simply a matter of updating the obstacle annotations in the scene, and you can see on the left and right how this is implemented. Finally, we used animation triggers, which are spatial cues that trigger animations that match the semantics that are labeled in the scene. And you can see on the right that we have different matching yoga animations playing for multiple characters. Finally, we carried out a user evaluation study. So this was a study from a real-world perspective that is somewhat reflective of current practices. So the participants were asked to complete a ground-up simulation using the Unity game engine. Due to COVID-19 restrictions, this was all carried out online. The users were asked to create a crowd simulation scene and then retarget this scene to a second scene. And 2 unique 3D environments were used. So each simulation required 7 explicit steps to complete before retargeting to the second scene, and structured and open-end post-task questionnaires were used to capture the immediate impressions of the software in action. And you can see here the results shown on this UEQ graph, which shows that the users generally found the tool stimulating, but the dependability of the tool was problematic, which could guide future research in this area, since our own experiences also reflect that sometimes crowd simulation tools, while technologically advanced, can be difficult to use in practice. For our time saving, we found that across participants, whether they were allowed to use our approach to retarget or not, when you see the 2 graphs divided, that around 50% time saving was reached for both. And this indicates a brief learning curve where participants were becoming more familiar with the tool set, and these findings are shown in the dependability metrics also in our paper. That's it from me. Thank you very much for your time. So in summary, we've presented a tool set which uses semantic information to speed up the creation and retargeting of crowd scenes. And we anticipate that with the proliferation of classification algorithms, there's great scope to leverage this in order to automatically annotate scenes and then use a platform such as our own in order to generate behavior automatically. We've noticed that there's a gap between research and practical tools as backed up by our user study. And the overall usability of our crowd simulation software was considered acceptable.